all 10 questions for quiz 1. Yeah. So when I look at your scores, not very good, overall, not very good. Yeah, because the number of students who got above 30, not many. Yeah, only a small number of students got above 30. Yeah, total 40 points. Yeah. I think about, so what reason? Because I noticed for each video, there are about 10 students not watching, for each video. Yeah, at least 10 students did not watch that video. Yeah, I just look at the number of views, 30, around 30, but two sessions of this class, we have 40 students. Yeah, we have 40 students. Yeah. So for those students who did not do well, yeah, that means you did not get above 30. Think about if you watch all the videos first. So that's the first thing, the bottom line. So because you need to watch all the videos, the minimum requirement. After that, then when you study the videos, the quality is important. Learning quality. Yeah. So if you do not really pay attention, so when you watch the video, so if you at the same time you do other things, so that's not good. So learning quality. Yeah. I heard, one student watched the video many times, at least some part of the video many times, that kind of learning attitude. Yeah, so that's probably the reason for that student who can do very well in this class. Yeah. All right. Anyway, I hope from the quiz 1, those students, so you can quickly improve your learning habit, because this is our first quiz. And we will have many assignments, and you will see many relatively hard questions in this class. Yeah, so you need to prepare yourself, for this whole semester. Yeah, try to do the best you can. Yeah. All right. Yeah, let me explain. Yeah, these questions. Some of the questions pretty easy, so I can go a little faster. Yeah, but some of the questions, a little challenging. Yeah, so I will give you a lot of explanation. Yeah. All right, so let me just, go through these questions in order. C.1, the first two questions. Yeah. All right. The first one, to evaluate a polynomial, it is always true that the higher degree it has, the more multiplications we need. For this statement, in order to be true, it must be 100% correct. Okay, yeah. So when we determine if a statement is correct or not, we like to see if it is 100% correct. Okay, yeah. If we can find a single counterexample, then it's false. Okay, yeah, here the answer is false because we know when we, so we look at the special polynomial x to the nth with n equals power of 2, right? Then by repeated squaring, we only need the k multiplications. Right, yeah. A relatively small number, yeah. But you know, it's very easy. You can find a number that less than n, smaller than n, but you need more than k multiplications. You need more multiplications. Very easy, right? Yeah, for example, when k equals 10, so you look, k equals 10, n equals 1024, but think about, you consider another number, let's say 997, for example. So to calculate x to the 997, definitely you need more than 10 multiplications, right? Much more than 10 multiplications. No. So here you just find one counterexample. So that's enough to tell us this statement is not correct. Yeah. When I first posed quiz 1 questions, I didn't talk about that repeated squaring. Yeah. So later, after a few days, then I gave the repeated squaring. Yeah. Yeah. But some students who did this question before, they know repeated squaring technique, but later you have time to correct it. Yeah, after you learn the repeated squaring, so you can realize, you need to change your answer. Yeah. All right, so that's the first question. Second question, is the execution time of a program a stable measure? Yeah, we mentioned this question several times in our lectures. Stable, we know it's not stable. The reason is for different machines, the execution times usually different. In general, different. Okay, so not stable. Then we switch to a stable one. Okay, we switch to, counting the number of basic operations. So we call it basic operations. Yeah. So that concept. Yeah. So answer no. Yeah. So this one should be easy. Yeah. All right. So that's the first 2 questions. Next 2 questions, number 3 and number 4. Right. Yeah. So let's look at the number 3 first. Given a computing problem, if you have an algorithm to solve it and nobody in the world can improve it anymore, then you can say that your algorithm is optimal. First, the statement is false, but let me explain why. Yeah. Here, in my description, in my statement, in the way I write this statement. I try to confuse you, I try to mislead you, go to the wrong direction, yeah, and check you if you really understand that optimality concept. Under what situation we can say an algorithm is optimal? Yeah. Here, I give you a description, the key part of the sentence. Nobody in the world can improve this algorithm anymore. Yeah. But still, here I like to say, even here, still not strong enough. Not strong enough to say this algorithm is optimal. Yeah. Here, I try to make you feel it is very strong to give you the information that it is optimal. Now, how strong it is, nobody in the world can improve it anymore. Right? It looks strong, but actually still not strong enough. Why? Nobody in the world. That means we mean the current time, right? We're talking about the current time, right? Everybody in the world, the living person, right? Each living person in the world currently, right? We're talking about people who are living right now in the world, right? Although so many people, but we just talk about current living people in the world. Yeah. Think about the situation. Yeah. Nobody in the world can improve it. How about after 200 years, someone can improve it? Right? Is it possible? It's possible. After 200 years, because our current people in the world still not smart enough. We cannot say, after many generations, the future peoples are not smarter than us, right? Nobody can say that. Future people, so definitely, in general, future peoples should be smarter than us because they inherit the knowledge we developed, but they can further develop new knowledge, new methods, new techniques. We do not know, right? Yes. So, and there are so many examples. There is one famous example called Fermat's last theorem. Have you heard of that? A very famous story called Fermat's last theorem. Okay, yeah. This theorem was solved after more than 300 years. Solved after 300 years when it is raised. Okay, yeah. Fermat, it's a conjecture. At that time, it's a conjecture. Yeah. So, and it was solved in 1995. Yeah, completely solved. The first time, 1993, that professor solved it, but there was a big mistake. Yeah. Then after 2 years, he fixed it. So we say officially, it was solved in 1995. Yeah. So in this example, it tells us if people in the world cannot solve one particular problem, still there is a chance that future people can solve it, okay? Can do much better. Yeah. So that is one angle to look at this statement. Why we say, so this statement still not strong enough to claim that this algorithm is optimal. Okay, yeah. But another related question, how do you claim that one particular algorithm is optimal? That's what we did in our finding the minimum question in our class. We use some convincing argument to show our algorithm is optimal by one method. By what? By finding a critical property. Okay, that way, finding a critical property, then we use this property, we can show no other algorithms can do better than our current one. Okay, so the one we use n-1 comparisons. Okay, yeah. For finding the minimum. All right, yeah. So that's a good example to show how to really prove our solution is optimal, because we showed nobody can use n-2 comparisons to find a minimum. Nobody can use n-2 comparisons. Even after 200 years, 2,000 years, nobody can use n-2 comparisons forever. Yeah. Our proof, yeah, we need to make sure our proof is correct. Okay. If our proof is correct, then nobody in the future, nobody can do better than our current solution. That's what we need for the optimality. That's the way we can claim our algorithm is optimal. All right, yeah. But the current statement in question number 3, that's not strong enough. Okay, so we cannot claim. Yeah, but here you can see if you answer this question just by your intuition, it may not be reliable. All right, because people can get misled easily. Yeah, because when you get some information, it looks strong, but actually still not strong enough. Yeah. All right, so that's question number 3. Yeah. Question number 4. All right. When we apply the greedy algorithm to solve computing problems, do we always get optimal solution? Answer no. Because the greedy algorithm, remember we have some discussion about greedy algorithm. We apply the greedy strategy. The greedy strategy locally. Yeah. The reason why we apply locally, because easier to do, easier. All right, easier, not globally. Okay, not globally. Okay, globally, then you have a chance to be optimal. Okay, globally optimal. Locally, the best choice may not lead to global optimal solution. Yeah, not globally. Why? Too hard. Too hard. Yeah. Okay. Yeah. Yeah. So that's the point. Yeah. The greedy strategy, that's the point. Some relatively easy way to solve a problem with some solution, and sometimes it's optimal, sometimes it's not. Okay, yeah. So here, 2 cases. Yeah. Optimal, if you are very lucky, then it's optimal. Okay, but in general, not optimal. Okay, yeah. Actually, most of the time, not optimal. But even not optimal, we do not say it's useless. Okay, we do not say it's useless. Not optimal, but if close to optimal, if close to optimal, slightly worse than optimal, still a good solution. All right, if it's close to optimal, yeah, very close, okay, still it's a good solution. Yeah. All right, yeah. So that's the value of greedy algorithms. You know, its value. All right, yeah. All right, so that's these 2 questions. Next 2, C.3, question number 5 and number 6. Number 5, which of following is the best to describe the overall efficiency? Yeah. I mentioned this question in class, yeah, because the best case efficiency, we know only one case, right? And this one case is the best you can get, okay, for all inputs, yeah, for all inputs. Yeah. Inputs, okay, yeah. You find the one, you need a minimum number of operations to solve the problem. That's the best case. Yeah. So definitely you cannot use this number to describe the overall efficiency, right? Because if you use the best case, you are too optimistic. Too optimistic, right? Yeah, worst case, also one case, but it's worst one, right? If you use this to represent overall efficiency, too pessimistic, right? So then you were too pessimistic. Pessimistic. tick, right? All right, pessimistic. Yeah, my spelling could be wrong. All right. Then average cases, because this covers all cases. All cases, yeah. And it's still not good enough. And we use the correct way to find the average. Okay, yeah. Remember, we use the weighted average. Weighted average. Yeah. That way, it is a fair way to represent overall efficiency. Okay, yeah. All right. Number 6. This one, if you use the correct formula, yeah, so then, yeah, the formula is given in our notes. Yeah. So here, I use one sentence. This sentence, I don't, oh, sorry, yeah, skip, yeah. Because this sentence, some students I saw before, they plug in the numbers. Yeah, so just in our formula. Okay, yeah. So I remember the formula is 1/2 p times n plus 1 plus n times 1 minus p. Yeah. This is the original formula. All right. But later we have a dominant term. I also wrote a dominant term for this one. So that is 1 minus 1/2 p times n. Do not use this one. Okay. Yeah. Because this is approximation version. This is approximation version. Okay. Yeah. Approximate version. And I ask you for an exact answer. Okay. Yeah. I'll ask you for exact answer. So you should use this formula, not this formula. Okay. And another possible error I saw from students before. Yeah, so they plug in number n equals 244, p equals 0.4. So they plug into this formula. So everything looks correct. Okay, the answer, as I remember, answer 195.2 or 0.4. Yeah. Anyway, yeah. 0.2 or 0.4. Yeah. I couldn't remember. Yeah. For example, all right. Yeah. But some students drop that fractional part. 0.2, drop it. Only give me 195. Because they argue the number of comparisons should be an integer. That's another possible mistake. That's correct. The number of comparisons should be integer, but when we talk about average, you do average on a group of integers, very likely your average won't be an integer anymore. All right. Usually your average is not an integer. Yeah. But if I ask you for the best case, worst case, then you can use this integer way, because the best case, the answer must be an integer. That's number of comparison. That's for one case, right? Worst case, or another integer answer. Just one case. But average case, after you take average, it's not necessary. You get an integer, all right, if we want exact answer. So you need to keep the fractional part. Okay, yeah, 0.2, yeah. So here I emphasize this concept, average concept, yeah. Because later you will see we do approximation a lot. When we do approximation, that's fine, yeah. If you give me 195 to approximate our final answer, that's good. It's a good approximation because you only drop 0.2, right? That's a good approximation. But our requirement here, we need the exact answer, okay? So don't drop. The purpose is I want to check your understanding of the average efficiency concept, okay? Yeah. If your understanding is solid or not through this example, okay? Yeah. All right, yeah, so that's another 2 questions. Next part, C.4, yeah, question number 7 and question number 8. Yeah, all right. Question number 7, yeah, because in class, I talk about Pascal's triangle, right? Yeah, so here, this question is designed to check your understanding of the Pascal's triangle. Yeah, so many of you search the web. Yeah, so if you are not familiar with this concept, you can search the web, find examples, so you can easily get the answer. Okay, yeah, but through this chance, hope you get yourself familiar with Pascal's triangle. Okay, yeah. So first, it's an interesting structure. Second, we can use this knowledge to help us improve our answer. Yeah, Pascal's triangle. Okay, yeah. Later we have another question. Yeah, we need to use Pascal's triangle. Yeah. So for this one, I do not, spend too much time to explain. Yeah. All right. Next question. Yeah, this one. Because after we learned repeated squaring technique and a repeated cubing technique, okay, yeah, the part E of module 1. After that, because in that part E, we spend a lot of time of module 1 about repeated squaring technique and the repeated cubing and the mixed way, right? After that, we also, because you can mix the above 2 techniques, mix the way, all right? Yeah. To get the best answer you can, to get the smallest number of multiplications you can. Okay, yeah. So the answer is 5. Yeah. But the ways to get this number 5 quite different. Yeah. So you only need to use one way. Yeah. So, all right, yeah, one way. All right. So let me just use a few ways to, to show you how to get this 5. Okay. Yeah. But before you work on this question, first you need to be familiar with part E of module 1. Yeah. Otherwise, it could be hard. I just guess if some students who did not watch video for the part E of module 1, very likely they couldn't get the correct answer. 24, oh, just 23. If they put answer 23, yeah, you just use the simple way. You didn't apply repeated squaring, repeated cubing, the mixed way, those much better technique. Yeah. All right, so here, 24. Yeah. Here I choose this 24. So you can get this 24 in many different ways. The first way, if we use the power of 2 structure, okay? Because we can easily identify, we can use power of 2, yeah, because 24 equals 16 plus 8. Yeah. 16, 2 to the 4th, 8 to cube. Okay, yeah. With this power of 2 structure, then we start with x. First multiplication, we get x squared, right? Yeah. Second multiplication, yeah. So let me put a circle, okay? That means the number of multiplication, yeah. X to the 4th. Second multiplication by squaring that multiplication, right? Yeah. X squared times x squared, okay? Yeah. The third multiplication, x to the 8th. The fourth multiplication, x to the 16th. Okay, yeah. So you can see after, yeah, so here, the cost we spend, so 4 multiplications so far. Okay, so that's the cost we pay at this point. But after you pay for this much cost, you have x squared, you have x to the 4th, you have x to the 8th, x to the 16th. All these power of 2 exponents. You have them. Yeah. You have them. That means if you need these numbers, you can reuse these numbers without any multiplication. All right, reuse them. Okay, yeah, because you have paid to get these resources. Yeah, so we treat these things. These are the resource. Okay, something useful. So what's the meaning of the resource? So we just treat things that could be useful. That's the resource. All right. Yeah. Resource and the paid, already paid. All right. Yeah. And it's in our pocket. That's your property. All right. That's our property. All right. They are our property. Okay. We are the owners. All right. We are the owners. All right. So here, that means x to the 24th equals x to the 16th times x to the 8th. When you use x to the 8th, no multiplication needed. So here, because this is the first time we pay, so we need to pay by 4 multiplication. For this one, 0 extra, all right? Because in this 4, we already covered that cost, okay? When we pay 4 multiplications, we cover that x to the 8th, okay? So 0 extra. Then this dot we need to pay, all right? This dot we need to pay. So the total number of multiplication in this way, 4 plus 1 equals 5. Okay, yep. So that is the, power of 2 way. So this way slightly different to repeated squaring, although the main part is repeated squaring, yeah. But, if we look at our definition of repeated squaring, different from this one, yeah. But that's not important, okay? We just want to find the best answer, yeah. Yeah. Another one I like to show you, based on the cube structure, yeah, because x to the 24, yeah, obviously we can identify x to the 8th times x to the 8th times x to the 8th. This structure, all right, yeah. This structure, we use the similar argument, yeah, similar argument from the previous solution, yeah. This time we calculate power of 2 through this x to the 8th, yeah. So we need 3 multiplications, yeah. All right, 3 multiplications. We do not do x to the 16th. So we stop after we get x to the 8th. All right, so that's our property. All right, that x to the 8th, that resource already belongs to us. All right, yeah. So we have the ownership on it. Yeah. All right. So next we use it with 0 extra. Okay. Yeah. Extra 0. We got already paid. All right. 0. All right. Yeah. But 1 multiplication in the middle, another 1 in the middle. So in this way, total also 3 plus 1 plus 1 equals 5. How about that? How about that? Equals 5. Okay. Yeah. Yeah. So the answer 5. 2 different ways. Yeah. So we get the same answer. Okay. Yeah. All right. Yeah. You need to be familiar with, these 2 techniques. Yeah. Okay. All right. And the mixed way, actually much harder. Yeah. So here I haven't give you a question that rely on the mixed way to get a solution that is better than repeated squaring only or repeated cubing only method. Yeah, because usually that type of question usually much harder. Yeah, so I do not go that far. All right, yeah. All right, so that's this question number 8. Then the last 2 questions, number 9 and number 10. Now, number 9 is the hardest in this quiz. Number 9. Okay, yeah. So I need to explain a little more. But the answer, if you pay attention, the answer I gave you in one of the videos. I gave you the answer. The answer is 3. Yeah. And remember, at that time, I gave you a thinking question. So that question, I ask you to think about how to get the answer. Yeah, I told you the answer is 3, but how to get that 3 number, that's not easy. That's not easy. Okay, yeah, but the answer is there. All right. Yeah. The answer is 3 comparisons. Yeah. So if we recall that question, in that question, I talk about n elements in the array with this n number greater or equal to 3. Okay, yeah. Then we need to find an element that is neither the maximum, nor minimum, nor maximum. Yeah. And remember, the first solution I try, not very good. Yeah, so the first one, because that probably the straightforward way that many students likely to use. Yeah. N minus 1, that's, first step for minimum, find the minimum. And after finding the minimum, then you find the maximum, but you can take away the minimum element by elimination method. So you only need n minus 2 comparisons to find the max. So the answer 2n minus 3, right? So that's the first solution. But I told you it's not good. All right, yeah, good. A good one, or we can say the best one. Yeah, so here, the best one, 3. Much smaller than this 2n minus 3. Here, for this question, yeah, I take n equals 1,000. Right? Yeah. So a relatively big number here, 1,000. Then even n equals 1,000, the answer still 3 comparisons, but I change my question. So I do not ask you, can we use 3 comparisons to find the solution? Yeah, although I can use that, but in that way, I just, connect to that example directly. All right. So here I try to, confuse you a little bit, or I try to hide my answer a little bit. Right. I try to hide that answer 3 a little bit. So I use this way to hide my answer. Yeah. Can we say that we can always use fewer than 5 comparisons to find this element? Yeah. The same thing, we know the solution 3, definitely we can, right? Yeah. We do not need to use 5 comparisons. We just need to use 3 comparisons. Yeah. Fewer than 5. Okay. 4, 3, 2. Yeah. So answer is yes. Yeah. But here I want to explain why 3. Okay. Why 3 comparisons? Yes. That's the trickiest part. Yeah, that's the trickiest part. Okay. All right. Yeah. So I need to, give you the thinking details here, thinking details for this question. Yeah. All right. First, we know to find the minimum or maximum. Yeah. Yeah. We only you talk about one. Okay. Minimum in and element array, we need n-1 comparisons, okay? Yeah. So when we start our old knowledge. So this is our old knowledge. We know this fact, okay? Yeah. n-1, all right. This solution is optimal. You cannot do better than this one, all right? Yeah. But, so if you look at the n-1 and the 3, far away, right? Yeah. So when n is large, here, 1,000, n-1, 999, much bigger than this 3. All right. Yeah. Yeah. So number 2, so we go one step forward. Number 2, all right, so to find an element that is not the minimum, not the minimum, okay? Negation. Here, we use negation here. Okay, negation, not the minimum, all right? To find element that is not minimum, we do not need to use that many comparisons, right? Yeah. So the number of comparison we need okay, this is a critical step. This observation is a critical step. The number of comparison we need, 1. How big is the improvement? When we, try to solve the negation question, negation problem, the answer is 1. So why 1? Yeah. Yeah. Pick any 2 elements. Let's say x1 and x2, okay? So we compare x1 and x2. That's one comparison, right? That's one comparison. And we can assume x1 less than x2, right? Without loss of generality, yeah. Because the smaller one, we just call it x1. The larger one, we call x2, okay? Yeah. Otherwise, we just switch, okay? x1, x2, all right? Yeah, all right. After one comparison, we know one element is larger than the other one, then the larger one is not the minimum, right? Yeah. So then our conclusion is x2 is not the minimum. Okay, all right, yeah, good, yeah. So you can see when we look at the negation version, we can do much better, right? Do much better, yeah. One comparison, we can find one element that is not the minimum. Yeah. Similarly, for maximum, we have the similar thing. One comparison, we can, yeah, so here, Yeah, at the same time, we can say, yeah, here, we still use this one comparison. X1 is not the maximum. How about that? Maximum. If one element loses once, it cannot be the maximum. All right? It cannot be the maximum. Yeah. All right. Yeah. Based on this critical, yeah, I said, so if you can get here, it's critical step. Critical step, then you're halfway to the solution because you need to do a little more work. You need to find an element, neither minimum nor maximum. All right, so next step, then we can work on our current question. Okay, find X, let's say, neither minimum, I just write min, nor max. All right. At the same time, yeah, so here, because simultaneously, yeah. Yeah, we need to consider min and max simultaneously. Okay, simultaneously here, I use this word, you know, I mean not separately. Okay, yeah. You have to put them together. Okay, not separately. Yeah. All right. Yeah. How to interpret it? So yeah, to get the important step forward, we need to interpret it. How to interpret it? Okay, yeah. So let me interpret in this way. We need to find an element that is greater than one element. Okay, this tells us greater than, not min, right? Greater than one element and smaller than another element. This tells us not equal to max, right? And this and simultaneously. How about that? Okay, yeah. These two conditions must be true at the same time. All right, yeah. So now you can see with this new interpretation, this is our new interpretation. Yeah. We need to do this. We need to, find a way to do thing like this. Yeah. Look at how many elements we mentioned here. Yeah. So question. How many elements we mention here. Okay, all right. Greater than one element, this is one, right? Yeah. So this one element, so one element, okay, all right. Smaller than another element, this is the second element we mentioned, all right. And then find an element, our solution one, number 3, okay? So we mentioned 3 elements here. Or we can say only 3 elements are involved in our interpretation. Okay, 3 elements involved in our interpretation. So when we have 3 elements, we have a chance to find one that is greater than 1 and smaller than another one. All right? Yeah. So the solution is with, analysis at this point, solution, select arbitrary three elements. In the array. Okay, 3 elements in the array. Let's say x1, x2, x3. Okay. Go find the one in the middle. In the middle, value in the middle. Value in the middle, we know, later we will call the median. This is the median concept. Okay. Find the median of 3 elements. All right. How many comparisons you need? Okay. Or here, because the number is small, or we sort it. Can we sort this 3-element array? 3-element array. Sort it. Okay. Sort it. The goal is we get x1 less than x2 less than x3. This is the median. This is the one in the middle. Okay. To sort it, sort the 3-element array, it's very easy to see 3 comparisons to sort. For the worst case, all right? Yeah. Yeah. Some students give me 2 comparisons because in the first comparison, they tell me x1 less than x2. Second comparison, they tell me x2 less than x3. You already sorted, right? 2, but this is the best case, okay? This is the best case, not the worst case. Yeah. Worst case, your second comparison, you won't get x less than 3. Your second comparison, you will get x2 greater than x3. That means you have not sorted. You need another extra comparison to sort it. All right. So that's one more. When you have this case, you need one more comparison. So the worst case is 3 comparisons to sort 3-element array. Then you have the median. The median is the solution we need because the median here, it beats x1. That means it cannot be the minimum. And the median, it is lost to x3. It is beaten by x3. It cannot be the maximum. All right, yeah, that's the solution. Think about, in this way, thinking in this way, it's so easy, right? Yeah. But to find the solution path, that's not easy. To find the solution path, that is not easy. Okay. All right. We only have 4 minutes left. Let me complete our last question in 4 minutes. Yeah. The answer is 3. Yeah. I remember I made a mistake. I only put one option 3 there because after I entered the answer, I need to enter the correct answer 3, but I forgot to change the question type. Okay. The question type is the multiple choice type, but I like to use the short answer type, fill in the blank type, but I forgot to change that. So then you see, that only, but if you select, just take that option, it's correct. Yeah. But why it is correct? Here, let me explain why it is correct. First, you need to identify the coefficients follows the Pascal's triangle structure. Pascal's triangle structure. Okay, yeah. Because follows Pascal triangle structure, then the conclusion is it can be written as 1 plus x to the 5th power. So the question, how many multiplications you need to calculate 1 plus x to the 5th? All right, yeah, okay, yeah. So let's do here. It's very simple. 1 plus x. 1 multiplication, we get it square, right? Yeah, first multiplication. Second multiplication, we get 1 plus x to the 4th, right? Squaring, all right? Now, because all these numbers we already have, 1 plus x to the 5th, let's just take 1 plus x dot 1 plus x to the 4th. One more, yeah, here 2, yeah. So the total equal 2 plus 1 equals 3. Yeah, so that's the answer. Yeah. But this step is important. You have to write, you have to be able to write in this way. And in one of my examples, I did a similar thing, right? Yeah. I did a similar thing because when I introduced that Pascal's triangle concept to you, I already used this, binomial formula. There, I call it binomial formula. This is the, binomial formula. Newton's formula. Binomial formula. Or some people call Newton's formula. Yeah. All right. I run out of time, so let me stop right here. And I will post the video soon. Yeah.